Hello, this is Masfin. Bonjour. Today I came up with a model which is called QSWAT. I used the model to run and see the result is on a catchment called Tugela Catchment. So I am here to show you some results. Actually, the opportunity what we can do with QSWAT model. First of all, a little bit introduction. I think QSWAT model is a model which uses QGIS as an interface. It's a plugin to the QGIS. It is a wonderful hydrological analysis model, which water and soil soil and water analysis tool is the full name of what SWAT means. Yes. So okay, where is located KwaZulu, the Tugela Catchment? The Tugela Catchment is located the KwaZulu-Natal province in South Africa, which is a wonderful site where all the gates are available. It's a research site, I think, for the University of KwaZulu-Natal Hydrology department. So I studied there, so I know the place and I have all the data and so on. However, the QSWAT model needs lots of data. Actually, the analysis, catchment analysis, and for example, estimating the runoff from a catchment needs lot of data actually, because so most of the models that developed, the traditional models or methodologies to calculate the discharge has some limitations. For example, the rational method work only for very small areas, 250 kilometers square, and use some empirical methodologies, coefficients, and so on. Actually, it's okay, but it's used for small catchments. And I also tried to run the HMS model on Tugela Catchment, and it's it also needs some for a bigger catchment, very difficult, I think, but I think I will try it again. But I have already successfully run it, and needs to validate and see, with the observed flows and so on, calibration, it needs some calibration and so on. But I have done it successfully on Tugela Catchment, and now I'm trying the QSWAT model, and the QSWAT model is very interesting because it considers lots of things. The land use, the soil, property of the soil, and the climate, humidity, temperature, rainfall, wind speed, solar radiation, all the things involved in the process of creation of runoff. Actually, SWAT model estimates not only the runoff but other sediment and nutrients, transported nutrients. It's a lot of things. But for me, the interesting part is the discharge part, the quantification of the water budget from the catchment, what we get, and see, if we can, we know if you are going to build a dam or anything like that, you need to quantify. You need to know how much water you get from the catchment, So for that, I just simply tried to run on Tugela Catchment, and I found the result. Before I'm going to show the result and everything in Tugela Catchment, it's better to show how we can run the model. It's the potential of the model, just using the exemplary data set which is given by the SWAT team, and a data that they created from a catchment. It's called in Ethiopia, it's a Robit. That's a catchment near to Tana Lake. So they have done it. It's very organized and perfect. It's good to show with it. How the potential of the model. So first I will show you that, and then I will show you the result, because running the Tugela Catchment, because it's very big, 28 to 29 kilometers square. It takes some time, but anyway, I already did it. So I will show you all the results. So actually, not to see the result, but the potential, what we can do with SWAT now. So that is it. So we are going to see run from the scratch the model using the data, Robit data, the Ethiopian catchment. Okay, then I will show you the Tugela Catchment. It's a very interesting model because it considers lots of things. As this natural process involves lots of things, it is good to consider, many variables to come up with, a reliable result that approaches the observed discharge. Although it is very difficult to run the model, because it needs a lot of data preparation, and it needs a skilled hydrologist to run the model, the SWAT model. It's not easy to run the model. It's not only to run the model, actually. Running the model you can run it, but it is also important to relate the variables, the data. What does it mean, relative humidity? What does affect the temperature? The interceptions, initial interceptions, the infiltration rate, catchment, the antecedent moisture condition, dry wind, the wind, whether it is, the speed, the dryness of the wind. Whenever the wind is dry, it picks moisture, it takes away. It facilitates the evaporation. When the temperature increases, the same evaporation increases. When the relative humidity is high, evaporation decreases because of the saturation, because of the equilibrium, you see. So lot of things are involved in soil property. Different soil do have different properties. Sandy soil absorb water. Clay soil, they do not. So runoff increases on the clay soil than on a sandy soil and loam soil, you see. So I am interested in studying SWAT because of a lot of things in it. Very interesting. So let me start analyzing or using the data, Robit's data, and see what we can do with it. Okay. Here it is. Test 5. Test 5. Okay. Okay, that in it. Great. Now we found, we see the catchment. This is a catchment that we are going to develop. Sub-basin, basins, and so on. And that is it. Now we have to process the river network. So we can make this one 0.7. This means a threshold. If a threshold means the number of pixels in the 1 pixel is 30 meters. The number of pixels that flows into 1 pixel. If the number, for example, 777 in our case, if 777 pixels flow into 1 pixel, then that pixel will be considered as a riverbed. That's what we mean by threshold. As far as I understood from the model I read. So that is it. That is the threshold we can define. We can increase or decrease, but let us try with it. And also they have already provided a river network. That was delineated from somewhere, so maybe downloaded from any, open map, or maybe that might be the real river, traced or something like that. It provided that, so that helps the model to guide as a guidance. So we can bring that riverbed, the true riverbed of the catchment, the ridge, So now we can create streams. This is the true streams. Then you see the model also do the same for us. This is a lake, Tana Lake, this part, and you see it is already made a network of the rivers similar to the one which we have given. So now the next step is to develop to give the outputs inlet. We can draw it here by ourselves, so we can import from the given shape file. They have already given it. We can draw it about ourselves. It's very easy. You can see. You just simply can draw it like this. It's very simple. So we don't need that one, but it is given here. Then the threshold means distance from the river, So we select this one as our outlet and give it, then it is selected. Then review the snap. the snap is okay also. Now we can create the sub-basins. Sub-basin, creating the basins, catchment. You fail to repeat the last version. Okay. Yeah, that's the difficulty of the. So this is a basins, you know. It's wonderful. We have done it. It means so we can also merge if we don't want, if the area is very low. If you want to merge this one, for example, this one with this one, with this one, you can do this. Press Control, click, and this will be. So that is it. Just save. Okay. So that is it. Now we can merge the two. You see, merge it. This one and this one, merge it. So that is it. That is the how we can delineate the watershed using a SWAT model. So now we can finish the process of delineating. As soon as the delineation process finished, completed, then the other step will be activated. Create the hydrological response unit. Is activated now. So now we will continue processing. We need still a data, land use map data. This has to be prepared by our service, land use. This one is I prepared for the Tugela Catchment myself. Soil has to be prepared. Soil, you see, soil data, soil map. Here it is. So now we need the lookup table also. This is 5 insert 10. This is just simply categorizing the slope in a certain step. From 0 to categorizing the slope. While it is calculating the catchment, it will show us 0 up to 5% slope together, the 5, 10, 15, 20, up something like that. So just simply that is it. Now we need to give this a lookup table that is also or must be prepared by our service. This is given lookup table. Okay, it's already made for us this soil map, and they also said that this one is the filter by land use. Soil slope is usually this one to make the response units, and also some consideration, like they say use 15 or 10, something like that. Then 15 something. This with these criteria, combinations, it will categorize the unit response units according to our wish, I think. So that is it. You create the response unit. Now as soon as the hydrological response units are created, then the other step will be activated. So it is activated. Now we connect the database, the SWAT database with the database. Okay, we connect them with this one. Connected now. Okay. Now we need to change the you know, the SWAT model has the data is for United States, so we need to put our data, local data, user data also. You know, it has a table where we can put user data, replace the United States data, it means, with our user data, and we can see, we can let me show you that. Okay, example data, not example actually, this is test 4, test 5 is our, you know, in this database we have some things to change. For example, user soil and then WG, weather generated user generated weather also must be changed. So bring this like this external data, we bring from that Excel a given one, and that is located well here. Now, our projects folder, test 5, notice that here. So user soil has to be changed. Click, 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 click. We say no primary key here. Click, finish. Yes, existing. Yes. Now the other file must be changed also. The same, this one needs to be the local one, you know. Didn't no. Finish. Now we have finished with changing the required files. Now we are complete. We can run the model now. So we can put this one as a monthly weather database, the one which we change it now. Rainfall, rain gauge, we have the data available in our projects. Example data says climate, you know, this is rainfall data. So rainfall, temperature also, temperature, wind speed, we can simulate it also. Yeah, I don't know how much it is going to be correct, but this is solar, then relative humidity, you know, relative humidity, solar radiation, radiant winds, temperature, everything is now done. So we can say okay, yes, process complete, perfect. Now we can make a table, create a table. No, for this is easy. So easy, wonderful. We are able to create the tables, build, select this, created, wonderful. Now it's finished. We already processed everything. If we need something in database change, we can change here. We can do lots of things here. But now we can run, my computer is 64 bits. So the date, just to minimize the from 2002 up to 2013, okay, so. And we change this number into 2 years or 3 years so that the model can run, begins 2 years, 3 years than 2002, it means. That is the model, you know. That's how it works. We can change this daily, monthly, yearly, but monthly is okay. So we can run, setup is finished now, and we can run the model with the data we provided. It means now it is going to run for us if you are lucky. Yes, we are lucky. So yes, the SWAT run, it was successful. finished. And we can read now the output files, you know, output files, element and so on. Let's import them. So we can run now. Let's run it, examine this with the model output. You know, this is the monthly steps and so on. This is output in picture, you know, very easy, visible, visual. This is the precipitation, the runoff surface, runoff 629, return flow, that means the base flow, you know, the ground flow, and other flows, everything, every information, infiltration, you know, the average carbon number is also given. The sediment also provided. Surface runoff millimeter per year is 620, something like that. Yes, in stream sediments, point surface sediments, other sediments, you know. So, the wetland is a negative sediment. What does it mean? I don't know. So that is a lot of information. That is the wonder of SWAT model. It gives you a lot of information. Point source, you know, reservoirs, if you have some reservoirs in the catchment, so if you include that, it also gives you information about your reservoir. So it's very wonderful model, you know. That's all. Now we can save the simulation 1. Save it. Successfully saved it. Now we can go to the fourth step, visualizing our data, you know, visualization. Rich properties, I think this one. See, for example, outflow, if you want to know about outflow. You see, this is the visual result. You can see the outflow of the calculated outflows in your catchment. What do you need more? It's just what you need for. So it shows you clearly. So it's wonderful. I mean, we can also animate it. For example, you can see clearly here that in the month of June, August, September is the rainy season in Ethiopia. During that rainy season, you know, you see the color changes. In June, you know, high rain, you know. That indicates the flow increases during those months. That is it. So it's wonderful. You know that. You know that the analysis is correct. You know, it's because in that month there is rainy season. We can also plot. For different basins. For basin 1, for example, outflow. Plot basin 2, also add basin 3, 5. Just simply to see the random. So you can plot it. Plot 1. You see, that is it. This is the flow, for example, this is flow 1, catchment 1. See, subbasin 1 is this one. See, subbasin 1. Wow, which one is 1? You know 1 here. Yes, 1 is here. You know that is the largest because most of the water has the outflow, we can say. The others, the green one is the reach 5. Green one is reach 5. Well, is this one, you know, little water there. with the figure. I can't see it. Okay, let me do it again. And let me repeat it. Okay, you see, that is the that is the number one, you know, the outlet, you know, in the months of especially, you know, you can see the 6 months, 7th and 8th peak, always similar. That is perfect. The result is very, very correct and it's wonderful. This is SWAT model. So SWAT model is wonderful. There is no other explanation, you know. You can see the results, visualize it, see it. You can also get in table format. You can take it into Excel and do a lot of things, you know, with it. So that is it. This is a very short example running the model, you know, QSWAT. There is also another ArcSWAT. You can use that, use the interface of ArcGIS also. You can also use ArcGIS, a little bit different, but the same thing. So this is the model, the QSWAT model. And now I'm going to show you what I did in South Africa. Okay, so we can say new project. We can exit the other existing project, that is Tugela. Test 2 is the Tugela I run. That is it. That is Tugela, you know. Yeah, I just I just minimize, reduce the catchment in order to minimize the processing time. That's why I just selected this part, you know. Tugela Catchment, Tugela River is the whole river that starts from. There is also another river that is coming from this Newcastle side. There is also another river that is called Moy River, also come from this side, and together they flow here to Mandini, the last destination. There is a weir there, a gauging station. So that's Tugela. Tugela is a wonderful place, you know, South Africa. South Africa is a wonderful place. It's a beautiful country. A lot of potential. South Africa is a wonderful country. And that is it. So this is the, you know, I delineated, I created the same similar step, the HRUs, Hydrological Response Unit, and you know, the inputs also considers. I have developed my own soil. For example, you can see soil, land use. This is my land use. It's a very land use. You see, this is my land use that I did. This is my soil map I did. So after doing all this, I ran the model, and I found out this. You know, you can visualize, you know, this is the results. That's, you know. Also we can, okay, we can see also the copy. Let's see if we can run it again. I don't know. That is, I just use this one. This simulated, all everything simulated, you know, because it is very difficult. So this create a table, select all, you know, run, So thank you. You see, that is it. So now we can come and run the model. This, you see, let us. So I had been there, and this is 2040, 2010 maybe 2040. Okay. I'll take 2 years there, as we did it before. That finish, rest, run the model. If you are lucky, it will run it. So it's so wonderful. We fun. Yes, now the result is, successful. So our read output file is, we can read is something like that. Yes, then run, examine. Successful. So you can see now the discharge, everything. So that's the catchment we selected, just for that catchment. The area is, I think, we can see the area. We can check it, but that is the return from surface runoff. Everything is just in precipitation, evaporation and transpiration. It's very, very sediment and so on. So this is the potential we can see. It may not be correct, as I have told you. It needs validation in the perfect data, the right data, local data. So we have to substitute that data we use here simulation, we simulated from. So that is it. We can visualize the for example, here you see simulation reach. You can see flow, inflow, outflow is delete, inflow, outflow, create. Yes, you see it creates. Now we can animate it also. Outflow, animate. You see, it's a matter of some. It indicates that. Actually, this might not be. Yeah, I don't remember the rainy season in South Africa. Well, it's possible to check it, but this is how we can see our results visually. We can do now for other catchments if the data is available, precipitation, all those data is required to run the model. So we can run on Tugela Catchment anywhere in the world. We can use SWAT model. So the knowledge, the skill, what we need to run the SWAT model is ArcGIS. Because we have to prepare the digital elevation model and know the QGIS. You have to have some knowledge about QGIS, ArcGIS, and also actually they are developing now the other SWAT Plus and so on. So it might be easier now to use. The data burden might be reduced there, but data preparation is the most difficult part of SWAT. So this is a SWAT. So you have seen it. It is a wonderful model. I hope you enjoyed the analysis. Actually, the idea is not to how to run the QSWAT and so on, but is to show the potential of QSWAT. it has great potential. It's a wonderful model. It's just simply, showing the model. Running the model, anyone who can prepare the data and know the steps can run the model. It doesn't matter. But the hydrologist, relates the data itself. Why we consider this data, and also interpret the results as well. That is the skill, the hydrologist stuff. So that is it. You know that the soil property affects the infiltration and so on. The humidity affects the evaporation. And the transpiration, that's interception in the catchment. All that land use activities affects whenever the land is hard to be penetrated by the rain, then the effective runoff increases. So that is a skill that the hydrologists have. They can relate, see the data, the effect of everything, the correlation between the interaction between the different attributes, we can say, and see the result, compare with the observed result, and decide whether it is correct or not. Estimation is not simply an estimation. You know that if it is exaggerated or not. Experience also tells you. You can compare the amount of precipitation with the catchment area, how much you are going to get is also estimated by experience. It's not a guess, it is an estimate, it is an experience estimation, You can estimate it also. So after the model run all the things that you provided, then you can interpret the result according to your experience and see if it is correct or not, if it is exaggerated or not. That is, I used to calculate the volume of a catchment with empirical formulas when I was in Eritrea, while calculating or building a dam. I use 10% of the rainfall, assume, you see. That is also just an empirical method to calculate the volume that is coming to the reservoir. 10% multiplied by the area gives you the volume, 10% of the rainfall. And I found it is okay. It's okay. It's alright. But that is rough estimate as compared to this one, So, merci beaucoup for your attention. Thank you very much. And I hope I'm going to come up with another hydrological models or calculations. Develop our skills through practicing. So that is it. Merci beaucoup for your attention. Merci.